to start. So hi everyone, bonjour à tous. Thanks for joining me. Like the slide says, my name is Larry Price. I work at Canonical on some of the new shiny parts of popular Linux-based operating system, Ubuntu. This afternoon, I'm here to talk to you about how we run classic applications in a confined ecosystem in Ubuntu. So what do I mean by classic application? And furthermore, what do I mean by confined ecosystem? Well, so let's start with a little bit of background. My job focuses on the idea of convergence, bringing the same Ubuntu on any platform, regardless of screen size, computing power. Convergence has driven us to build a lot of really cool software over the years, discovering new concepts of security and usability from a different perspective. While we want to take advantage of these new architectures and toolchains that we built, we also want to take advantage of the treasure trove of stable, mature software available in the archives, and we want the use of that software to be seamless to our existing users. So a classic application in this context is any application that I can currently install with a traditional package manager, with an active package or a software center, and then run using either the terminal or a graphical discovery interface such as Unity Dash. These applications can be terminal-based or graphics-based using X11. They're applications we've been using for years to make our Linux desktop experience complete. Apps like Firefox, LibreOffice, the GIMP, and games like Zero AD, Pingus, and many others. Without these apps, it would never be a year of the Linux desktop, instead of every year being a year of the Linux desktop. And though some applications have already been migrated to new display servers and new packaging systems, this talk will be focused on those which have yet to be migrated. Classic applications were designed to be installed and used in an unconfined ecosystem. The way that applications have been traditionally installed and access resources has grown organically alongside the tooling and other parts of system management. And throughout this process, applications can or must access parts of the system that they are never meant to access. And malicious software could easily snoop on private business with benign applications. This is not only a show on desktop, where you're likely checking on the machine once a day or so, but also a potential threat to internet-enabled devices, which are infrequently updated or checked for health issues, and could be scattered throughout your home. Dependencies are another place where classic applications run into problems. Typically, apps depend on several other packages, and sometimes those packages can conflict with other versions of packages installed by other applications. Worse, sometimes applications need newer versions of packages that aren't available on the system, or similar package versions have different patches on different distros, leaving the application holding back changes until a newer application version becomes available, which may not be until a distro makes a new release. This could be preventing users from running the best version of a piece of software at any given time. On top of that, we also see an increase in the pollution of our root file system, and this is hard to read, but this graphic is a great visualization of the way that the Linux file system looks. But you may notice that it's pretty complicated, and some of these things are a little bit redundant. For instance, this is the contents of dumping my path variable. We mean they're user runnable binaries, and bin, sbin, user bin, user sbin, user games, user local bin, sbin, and games, and any number of dot directories in my home directory, as well as Heroku sneaking in some random user local Heroku bin. And similarly, library and data files appear wherever they want. These are the results running lgconfig on my machine, though I'm not considering this complete list. And data directories are just kind of wherever they need to be. So, to generalize the goal of confinement, we want to move away from letting apps snoop on each other without permission, and we want to take back control of our file system, putting these applications in a known location, and giving each application the appropriate dependencies. Our traditional package manager and Debian-based operating system, Package, is over 20 years old and carries the weight of those years on its shoulders. And because of this, we thought it was best to introduce a new packaging toolchain. So historically, a couple years ago, Canonical announced clip packages, which were kind of a solution to this problem. An application package and click is bundled with any specific dependencies that it needs, and it takes advantage of frameworks to access any shared resources that it might need. It also uses AppArmor to create a confined application and specify any security features that you need. Clicks were used to package applications for the initial round of Bluetooth touch devices, giving them a little bit of headline. These devices ran Mir instead of X11, as well as Unity as a display server, which sort of gave us our confined ecosystem. But these tool chains were missing some important features and lacked maturity. So fast forwarding to today, we've seen the emergence of snap packaging, also referred to as Snappy. Snappy is essentially another iteration on clicks, doing better version management, sleeker application confinement definitions, and new ways to interface with system resources. You can use snaps today on modern Ubuntu or several other distros. Snaps will all live in a special root directory and can be completely confined when installed from stable channels or unconfined when installed from unstable channels, if you must. Snap apps come bundled with all of their dependencies locally, meaning that all apps will have the dependencies they need and upgrade whenever they want. No longer needing to wait on package maintainers to get them into the distro. Snaps are automatically updated once a day, taking the pressure off of the user to keep their system up to date. And snaps come with the option for Delta updates, which means that the toolchain can download your diff instead of an entire package, potentially making downloads smaller and faster. And as confinement is concerned, snap apps are relegated to their read-only piece of the process by default, requiring interfaces to be connected to perform system tasks such as reading the display, using audio, and using the network. In snaps are used in a hybrid or classic environment, in addition to a traditional package manager, we can continue to pull in and use our classic applications while enjoying confinement and security in our migrated apps. However, one exciting premise of snaps is the ability to run in an all-snaps environment, which we, I think, call winter personal. Yeah. But this puts us in a bind. We can't run classic apps in this all-snaps environment. Our good old classic applications are looking for an unconfined system, and we're looking for the X11 display server. In this all-snaps environment, it's prepared to give them neither. We need a way around this issue to allow users to run applications just like they would in a classic system. So to resolve this, we've been working on a suite of tools which we call libertine. A libertine is a person who acts without moral restraint. Libertinism is an extreme form of hedonism, living one's life for pleasure while only thinking of oneself. In a sense, our classic applications are practicing libertines, and it's our job to pull them back into moral high standing. These applications need a safe place to go wild while the rest of the world falls in line, and we provide the safe space as a Linux container. Containers are generally unrecognizable from a traditional Linux desktop experience. A libertine container has its own file system to work with, and binds to system resource directories to access things like home and some system resources. Internally, we continue to use apps and dpackage to manage our packages, even when the host system is not allowed to use dpackage, even if dpackage is installed on the host system. Libertine also connects to a program called Xmir, which allows us to run an X11 window isolated on top of Mir. Every installation, removal, and system modification is done internally, protecting the outside world from whatever these classic applications may be doing with the file system. In the Libertine suite, has many parts to extract away the underlying implementation of classic Ubuntu as best as possible. C++ library and GUI, Python launcher to command line interfaces, and tools to control other aspects like launching Xmir and to control a clipboard. I'll go over a few of these now. Again, a little difficult to see. This is just JSON, dictionary and arrays and all the good JSON stuff. So Libertine uses JSON as a database file, keeping track of all installed packages, creating containers, modified bind mounts, and we just use it as a database, maintained individually for each user on a system. And using JSON, we found lets us not depend on any database frameworks, which is good. for our use, because then we can also just ask users for the raw database file, and they don't mind if there's 30 or 40 lines of JSON. And so the crux of our container management is our Python library. Of course, it contains an abstraction around the database that we just saw and utility functions, but the primary use is to abstract away the process of handling different implementations of libertine containers, of which we support 3 types: Chroot, LXC, and LXD. Chroot is a special case maintained only for use on devices with kernels too old to support LXC or LXD. With the Chroot backend, we use the filter command line tool to create a base domain system and a user's home directory as a Chroot jail from which we'll run all of our commands and applications. And when running commands within a Chroot, we use a tool called proot. And we'll generally try to run proot unprivileged to run that command within our Chroot jail, but every now and then we have to run privileged Chroot commands. And so we prefer not to use Chroot commands for containers. We consider them deprecated, though it's still useful. But LXC containers have been our preferred container type for most of Libertine's lifetime. LXC combines the kernel C groups and support isolated namespaces to provide an isolated environment for applications. LXC tools basically enforce the copy of the home directory. Oh, no. I forgot to unmute. Oh, no. I'm sorry. Sorry to listeners at home, I guess.
We should start from the beginning.
No, we're capturing the sound from the camera, but it's just not perfect.
Okay, thank you. So we create unprivileged LXC containers, setting up the host user inside the container so that we get access to home and system directories, and setting up unprivileged LXC to integrate with traditional desktop features can be tricky. And we go to great lengths to ensure that we can access things like audio through the system. I'll also note that the LXC Python API is quite mature and works relatively well for our needs. For instance, this is a code sample showing how we use the LXC container attach method to run our commands within the container and pure Python. But the newest, shiniest backend for Libertine is LXD containers. LXD is a new face on top of the LXC implementation, simplifying container management and frequently providing speed and usability improvements as well. Libertine LXD containers are outliers in that we depend on the LXD backend to maintain the root file system, though we still maintain locally the user's home directories and mobile applications directories. For the most part, setting up LXD is just like how we set up an LXC container. We bypass several devices, map the current host using the system, and it's also default packages. One weird thing about LXD is how we have to set up /run/user. /run/user is a system directory for storing files or running processes when LXD container starts. This directory, unfortunately, is overwritten completely when it starts, so we need to remap it using some starter scripts. To work around this, we create a custom script and copy it into the container. This script creates missing directories, fixes permissions, and remaps things like /run/user to ensure the system is in order. We add the files to the container using the Files API, which is back there, which is part of the Python LXD package. But the Python API for LXD is not quite mature enough that we can use it for all of our use cases. So we use a hybrid solution to the Python API and calls to beopen to start processes manually. As an example here, we use the Python API to update those devices. It's just a dictionary, and we use the Python LXD API to create this profile, update the dictionary, and save, using LXD exceptions to tell us when there's an error. On the other hand, when we run applications, we have to use psd-open to launch applications, because that's the best way for us to run LXD applications in the background while still getting all of the output in the foreground. So we also have these services that are responsible for making sure the containers are started and stopped appropriately in LXC and LXD. This is to help us save battery life so that the containers aren't started all the time. And it ensures that when a user stops one container, or stops one application within a container, the container doesn't stop, but we wait for all applications to be closed. Moving on to user runnable binaries, we have a Python library, or a Python binary called the Container Manager, which allows users to essentially create and manage containers and install packages and modify by mounts. This is a basic overview of using the libertine Container Manager to create a container. It's fairly straightforward. We just call them create subcommand with any number of flags, all of which have intelligent defaults except for ID, so the user doesn't have to know what kind of container backend we're using. Here I've shown that as just a black box, and then it just updates the database and adds all of the file system things using the given containers backend. And this is similarly just what installing a package would look like. Note that a package name may not line up with the binaries installed, but we're only keeping track of what the user explicitly asked us to install. Because the purpose of the Container Manager is to prevent the user from having to deal with the low-level concepts of any particular container type or package management system, and focus on the key concepts of creating and installing. We also have a debug service written in Python to replace the work being done by the last application we saw, although this isn't fully implemented yet. But many of the commands that we use in the Libertine Container Manager take a very long time to run, and bad things will happen when those commands are interrupted. For instance, stopping debug, which of course will cause, or can cause, broken packages to appear in the system. Libertine D aims to solve that by being a completely asynchronous method where we use Python threads and send updates through debug signals. And although we would like to replace the Libertine Container Manager backend with this in the future, we currently just use it to list container paths and application IDs. Which brings us to liblibertine, which is the root of discovering container information for several external libraries. It's currently a wrapper around a client for Libertine D, and many of the low-level libraries that access liblibertine are written in C++. And liblibertine gives them a convenient way to access libertine information without having to talk directly to dbus. The code sample seen here is just us making a simple dbus call from C++. We also have a GUI written in C++ with QML. This is an easy way for us to manage containers and even allows us technical users to be able to easily manage containers and install packages. It's mostly a series of lists showing you can see it in a list of containers in which you click through the list of packages. For the most part, functionality in the GUI is the same as it is in the command line tool. And now the real meat is Libertine Launch, which is a Python tool that we use to actually launch applications. What Libertine Launch will do is clean up the environment for running apps and then forward that environment to the container implementation to actually run the application. Libertine Launch can be used from a terminal, but we generally prefer it to be used from a launching tool, like in Ubuntu and Unity 8, we use it with Draft Launch. Pasty is a daemon. It's a companion binary to help applications use the clipboard. We just use cute signals and swaps to wait for copy and paste events from the underlying content hub, and then we forward those events to our X11 apps. And in doing this, we can use copy and paste pretty much like we would in these applications in a classic desktop. So what actually happens when we launch applications using Libertine? By clicking our desktop icon, we'll call Libertine Launch with a container ID and application exec line, which was properly found using liblibertine, which found that information using Libertine D. Libertine Launch will then start utilities like pasted and xmirror. It'll set up the session by cleaning up the environment and setting up a whole bunch of sockets to communicate between the two. And then it will launch a container instance based on the Python library, which will then do any number of things based on the container type, like update line mounts, launch a window manager to connect to an instance of X, and finally launch the app. And that's most of the full picture. To review, we build a container using one of the Libertine tools, and we set it up to install applications through app, even when app isn't on the system. Libertine keeps a container, and its classic application is confined to their root file system in small holes in code to let them access things like the home directory and resource directory. At which point something or someone can launch the application via Libertine launch, which will prepare the container environment to mirror the host, show the window manager inside a container connected to the host display variable, and launch applications. Given all of that, where can we actually use Libertine? The answer is, well, in most of our modern Ubuntu systems. Unity 7 is the current default desktop session in Ubuntu, and using Libertine in Unity 7 is a little bit silly because Unity 7 is not a confined environment. Already runs X11 and already installs the package to package. But I think it's worth noting that we can use Libertine just as well here in order to allow users to run their applications in a confined container without mucking up their system. Because Unity 7 was already running X11, Libertine's classic apps can use the running X server to connect to their window manager. So we don't need any special tools for that. And because Unity 7 is not a target platform, applications in Libertine containers are automatically discovered by the Unity dash, so you have to jump through some hoops to get them to show up, either by writing some definable desktop files or by manually launching Libertine launch. Alright, so Unity 8 is a new and improved version of Unity 7, running mirrors as display server instead of X, and pre-installing Ubuntu. Desktop Unity 8 is also not particularly confined, but running mirror instead of X alleviates some of our previous security pains. Mirroring Unity 8 can run some applications natively, such as modern Qt apps, but are unable to run all of our classic apps natively just yet. And Libertine works well in Unity 8. And it's built into the application discovery logic. As in here, search for Pingus and it's come up. Click on icon for Libertine classic app and the bring Libertine launch, just as we normally would, except in this case, there's no X11. So the system will also start an instance of Xmirror for our application to attach to Window Manager too. Xmirror allows us to run X11 apps in an isolated window on top of Mirror. Each running Libertine application will get its own Xmirror, bringing online communication between the apps. And with this step, we successfully launched X apps in a non-X environment. So, similarly, Ubuntu Touch, Ubuntu Touch also runs Unity in Mirror, and therefore can't run classic apps on its own. Furthermore, users were prevented from using active packages to install apps due to Ubuntu Touch being a filing system by default. So even apps that would work in a desktop Unity 8 sessions might not be installable and runnable in an Ubuntu Touch session. And with varying hardware and street sizes, classic apps don't always run as well on Ubuntu Touch. But on some devices, like the PQM10, we pre-install a Libertine container with some essential classic apps such as LibreOption Extract, and we found that they work just fine, and it gave us a peek at a truly convergent environment. Of course, we use Libertine almost exactly the same way here as we did in Desktop Unity 8, launching and attaching to an Xmirror instance. Because the older kernel on the inside requires the use of a container, which is one of the reasons we use the group-based containers around. Alright. So our end goal has always been to run classic apps in a completely confined ecosystem, which brings us to snaps. As mentioned, snaps are a packaging system to allow complete deployment. In which your personal, the system provides only snaps. In packaging Libertine with snap, we build Libertine from the source, conceal and create one large package file. We need to update some padding and environment and variables to be more flexible for snaps. And we need to make some architectural changes to Libertine and Libertine B. Snaps also encouraged us to hurry the production of our Libertine container backend because there's Libertine snap available that we can use. In order to access resources in snaps, you have to connect to the interfaces, and we connect to quite a few. This is a short list currently that we use. LexD, obviously, connect to LexD. Network and network bind to connect the socket to the network. Home to connect to the used home directories, and all the rest of your standard graphics. Okay, live demo. This never works, right? Well, plot twist. I've been running this presentation in Firefox running a Libertine container and Snap the whole time. so it works. But it might be interesting to also run some other applications real quick. Something like X11. More come up. That's not too well, isn't it? And we can say Firefox, and you can see the command that's being run within the container. And this is running completely isolated in its own root file system, completely separate from the host. What else? Let's see, we can run something like LeafPad to edit documents. And I can open something that already exists, a test file, and it all stays fine. And it doesn't crash, which is good. And one more, how about some Minesweeper? And there, well, we're pretty good. We got 200.
This is on Unity 8?
This is all in Unity 8, yeah. So yeah. To be clear, this is Libertine running on Unity 8. Libertine is a snap running LXD containers. And with that, we can go ahead and finish up. Oh, wrong. Ignore that. To very quickly review, we wanted to be able to run classic desktop applications in a fully confined X11 ecosystem using a packaging format, and we use Libertine to do just that, mostly through Linux containers. And there's a bit of wizardry in the back end with snaps, and we have this working on a lot of our modern machines. There's obviously a lot that we're still working on. All of these things, Unity 8, Mir, and Libertine, and Snap, are all moving at a mile a minute development-wise. And a lot of stuff's still broken, like we have trouble with a lot of apps that use dbus. Our Snap's pretty big. I recently think I might have made a regression where audio doesn't work in the Snap, but that's called working too hard on that demo. And that's it for me. Yeah. Thanks for listening. That's all my contact information. I think we might be out of time.
Right on time. So,
Right on time.
Tomás wants to set up. Rory can ask some questions, but they will not be recorded because the recording is cutting the email.
Okay. So is that so we can do questions? So are there any questions? Yes.
All of the apps are running in the same container, so there is one Libertine container.
Right. So the system is made up such that you could create as many containers as you want, and then our underlying backend will know which container ID to feed, which container is the right one to run the application in. All of these are running in the same container. And so if you want
I
like
thought it's what you said that people came together was like one application tries to create together.
Each one has its own separate text.
right, so they all run. So we work around the problem with snooping on each other.
Does anyone have HDMI to DHDA app that we can borrow?
Yeah, so like we prevent the apps from talking to each other through like X11 by using individual instances of Xmir and I think you can go ahead and unplug probably. And so each application will have its own Xmir that it's running out. But they can still all talk to the same file system. Yes. What about Cleveland? No comment. Although I'll say it's nice to have a diverse ecosystem of new display servers and packaging formats on the horizon. Anyone else? Okay, thank you.